Yep.
So we have to make the project if we use Coblox. We can't just open a .c file in Coblox and start, messing with it. Or I know when I first opened the zip file, I just double clicked on it and asked me, do you want to open with Coblox? And like that, it was all there.
Oh,
But
okay.
I'm just wondering if that would cause an issue though. I haven't
Well,
really tinkered with it yet.
so you can run the program and it's running.
Yeah, I just opened up main and it run and showed exactly what you have there. The U is equal to dot, 000.
So it picked up ATOF, and the header file
Yes.
automatically.
It's because it was all in the same folder.
Oh,
So I was
okay.
wondering if we need to make the project or not.
Interesting. So let me see if I can replicate that process. So we'll go ahead and start a new project again. So did you get a new project or did you try to import?
No, I just double clicked up the .c file and it opened it up as just a C file instead of a project in Coblox.
I see. Okay, so let me close this first because I forgot to turn on the recorder, so I might as well just repeat this whole process. So let me go back to the folder itself. Okay, this is still here. Okay, so let me get back to the folder, and I'll nuke the folder itself and unzip the zip file again. So when you just open the file.
Yeah, I just had it open in my on Windows and
Okay.
contents in the folder. I opened up main.c.
Okay.
And just hit build and run to see if it would work. And it did.
Now, did you open main.c or did you open the folder itself?
After I unzipped the folder that you gave us, I
Yeah.
just opened the
Main.c in the folder?
main.c, and
Okay.
I opened it up in Coblox. It just asked me, do you want to open the Coblox, share? Yeah.
Okay.
So it was like that.
But it should not run. Oh, you know what? It still runs because.
Because it's like the default setting. But all I do is build and run the C.
Did you do it in Windows or in Linux?
In Windows.
In Windows. Okay, that's
No,
kind of
Windows
suspicious.
I'm just wondering, would that cause issues if I didn't build the project? Probably.
No, because I think it's doing it by itself. Yeah, go ahead.
I did that for a long time, and it will build this file, but it will not build your ATOF file.
Oh, okay.
And so then it will just continue to use the one that TAC included. So any changes you make won't propagate in a build process.
Okay.
Okay.
Without it being in the project.
Okay.
Gotcha.
Does that make sense?
Yep.
That's what I wanted to clarify. Thank you.
Yep. Yeah, I personally would just kind of build the project itself and make sure that those source files are included in the project, and then let the code blocks deal with the dependencies.
Okay.
Yep. Okay. So that's the logistics part of it. How many people used code blocks in cisp 360 or 400, 430? Okay, so good. Okay, so you guys probably know more about code blocks than I do. Because I started using code blocks like a few days ago. Because of this class. Yep.
So I tried downloading it on my personal computer and using it, and then I realized that you have to get the version that has the compiler built into it.
Yep.
So if anybody else does that,
Okay.
make sure you don't make that mistake.
Okay. Thank you. All right. All right. So the next thing, so this is basically from the logistics perspective. How do we set up a project so that you have the source files that you can play with. And one thing I do want to recommend people to do is not to use cout or printf as a debugging mechanism, okay? Because that really is it can only get you so far. I would use a breakpoint. So if you click on the, I'm not sure whether you can see. Can you see two levels of shade of gray here? This is white and this is kind of light gray. If you click on the light gray portion, you can set up a breakpoint. Okay, so the idea of a breakpoint is you can stop, when execution gets to that point, it will stop and you can examine variables. So I'll give you an idea of how to do it. Let's see, active debugger, target debugger. Okay. See, I haven't used this tool before. Build and run. I'm not sure whether it does it automatically. No, it does not. It doesn't really stop at the breakpoint. I think you have to set it up to retarget for debugging. And this is not a project yet, and that might be the reason too. It's not a project. So you might need to turn it into a project first in order for the debug option to be available. Because if you remember, when I imported the files into the project, there was one checkbox to say, do you want to include debug with this file? So that will set the compiler option to whether to include a simple table or not. So that's why when you run it like a simple file, it doesn't work the same way. Okay. All right. So any other questions about this? So I do want to, yeah, go ahead. Question?
Yes.
Yep.
The conversion of real number into floating point. Can you give us just an example of it? Because we are not going to use that flat type. So.
Okay, so that's a good question. That's in fact is the purpose of today's lecture,
Yeah.
and that's why I wanted to make sure the recorder is on, because I think today we will get a better insight into the homework assignment than last time. Okay, we'll go through some of the examples, but at the same time, we also have a much more systematic way of describing what we are doing. And that's more general, and you should be able to convert any number and not just the tricky ones that we come up with the other time. Okay, so the recorder is on, just want to double check. And we'll go ahead and create a project because I do want to show you how to use the tools. So we will use a console application. Build target is console files. Okay, so we'll go ahead and use this. And I use C, if you want to use C++, as I said, you have to be a little bit careful. So we'll name the project ATOF and folder to create project in, because it will automatically create a folder called ATOF, so I have to back it up one level. And you can see the path is now just going to ATOF, which is the right place. Create debug configuration. You do want that. That's a useful one. Release, that's fine too. And then click finish. The wizard is about to overwrite the following existing file. No, we do not want to overwrite that file. Okay, so that means it is preserving this file, but this is not enough because we have another source file to include. So right click on the project itself and say add files. And this time we're going to add atof.c and ufi.h as well. You can control click and select two files and click open. Select the targets this file should belong to. Debug, yes, we want to be able to debug inside ATOF. So that's it. So now we have all the files included, and let's see if the breakpoint works now, because I can now go to debug, and this is great, okay, because it's definitely recognizing that we can debug this program. So we'll go ahead and say, yeah, go ahead.
The file.h is not added.
So say that one more time.
The file next to atof.c. What was the other file that you were talking about? .h.
The header file is here.
Oh.
Yeah, I control click and I included two files in one single action. Yep. So when we use it this way, you can use debug and say start or continue, and what it will do is, okay, the perspective has changed. You want to save it? Yes. So now the program execution is now paused. In other words, at this point, I can look at the variable u and find out what's in it. So we can go to debug, and let's see, how do I...
There's a, or at the bottom, it says command.
Yep.
Maybe.
Is that GDB command? Oh.
GDB right there.
Okay. I think it is either debug or inspect. Let me look at all these options here. Doesn't look like that's the one. Plugin, settings. Okay. If I just look at U and right click on it, let's see what's going to happen. Ooh, there we go. So you can look at this and watch U, okay, which means you can look at the actual content of U, but it doesn't have like anything like print U. Okay, so we can look at U as a union, and if you click on this, it will show you the F component is this, and then the I component is this. Okay, which is basically my way of doing the conversion between a binary using the same binary representation. One is looking at it as an integer, and the other one is looking at it as a double precision floating point number. Okay, so that's kind of working. All right. Okay, this is all new to me because I can show you what I'm used to. Now you guys don't want to know that, do you? Because this is all new to me. Okay, so but using a debugger is the best way to debug your program, because when you debug your program, you can stop the program and then examine the variables, and you know exactly where you are. So that really helps. It's much better than printf, because when you use printf or cout in your case, if you use C++, when you use cout and you say, oh, but I want to know what is going on right at that point, you have to go back, insert another cout statement, recompile the program, run it again, right? And then you end up with a whole bunch of couts. How do you know which one is which? Well, now you have to make sure that each cout has its own unique prompt, so that you can tell, oh, this cout is coming from this line, this cout is coming from this line, and so on. Okay, it's not nearly as helpful as using a debugger. Okay. All right. So if you guys want to talk more about debugging, we can talk about it. But I do want to kind of proceed to talk about the conversion process itself, or at least the math behind the conversion. So this particular module is titled exactly what it is supposed to do: base 10 scientific notation, which is what you type. The string input into ATOF is in base 10 scientific notation. And we want to use that string and convert the number represented by the string into a double precision floating point number, which is the topic that we are in right now. Okay, you can print out the PDF version, okay, if you want to put one into your binder, or if you just want to read it, it is much easier, just read the HTML version. Okay, so the first part is about parsing, and you have seen this part already. I have inserted a backslash in front of the first plus, because this one is representing the actual plus symbol itself, as opposed to this one, which is representing that we have at least one digit here. Okay, so this plus here means we have at least one of whatever is preceding the plus. And this one here is saying we have any number of whatever is preceding it, which means you can have a single period, but no number, no digits after the period. Is that okay? Are there any questions about reading this particular syntax description? I did not invent this particular syntax description. It is used a lot in many other languages. Okay, so when you look into SQL, look into some of the other programming languages, a lot of times syntax itself is described using something like this. If you are into regular expressions, you will also find that in many editors you can enter regular expressions using pretty much the same standards. The asterisk means any number of, and then the plus is at least one. Yep.
Shouldn't the plus after the E also have a backslash?
Which one?
The plus after the E, shouldn't that have a slash in front?
Yep, that one should also have an E. Thank you.
All right.
Yep, good job. Yeah, he's talking about this one here. There should be a backslash in front of it too, because this one is not indicating that we have at least one open bracket. It is basically saying literally we can have a plus sign here. Okay, but I think we know and we understand enough about scientific notation that this really should not be a big issue. Okay, so moving on, I personally wrote this program, and I find it to be useful to define a structure first. And because most of you went through a C++ programming class, a struct is kind of like a class where all the members are by default public. Okay, so you just look at it that way, and it's no different. It's no big deal. Okay, so I'd like to define a structure like this because it is kind of like a bundle of things that are related that I need, for all the subroutines. So instead of passing like 5 or 6 different parameters, I just pass one single parameter because it's a pointer to a structure. So from the pointer, I can now get back to everything that I need in order for the subroutine to work. So I personally find it really helpful to have a structure to do this. So the structure itself has multiple members. This member is a pointer. Basically, it is quote unquote a cursor. It tracks, okay, what is the next character in the string for me to process. So as you call the subroutines or as you process the characters, this pointer will advance to the next one, to the next one, to the next one, and so on, because it is keeping track of your progress, okay, how much of the string is already processed. We have an integer that is just a single, this one doesn't even have a width description, because this particular integer is either 1 or -1. Because its only purpose is to remember, is the number negative or is it non-negative? Okay, so I don't really need to specify is it 16-bit wide, 32-bit wide, or 64-bit wide, because all I need is to represent 1 versus -1. The next one is the mantissa, but this is the mantissa in base 10, okay, but without the decimal point 2. In other words, if you look at the mantissa of a scientific notation, you take out the decimal point, what is left in the mantissa in the string is now in M. Okay? And then we have E, which is the exponent. Because we can only deal with in base 2, we can only handle up to 2 to the power of 1024. So, you know, a 32-bit integer is more than enough to deal with the exponent. Is that okay? All right, okay. So using a structure like this, the parser can now be broken up into smaller components, and I personally would use one function for each part of the scientific notation. When I did this program myself, I have one just to deal with the sign, one to deal with the mantissa, and one to deal with the exponent. So this way, you know, each subroutine is only about 10, 15 lines at the most. It's easy to read, easy to debug. Okay. And from the main subroutine, not the main subroutine, but from the perspective of ATOF, it is just 3 function calls and you're done with parsing. So instead of cluttering ATOF with the parsing logic and all the details of parsing, now your ATOF looks really clean because it's just 3 function calls, you're done with parsing, and then you can focus your energy to the actual conversion from base 10 to base 2. Are there any questions about this recommendation? As I said, it's a recommendation. If you decide to use a monolithic ATOF, which means it's one single subroutine that doesn't call any other subroutines, you might guess. I'm definitely not opposing to self-torturing. Any questions about this part? But my recommendation is this because this is how I wrote my program, and I found it to be easier to manage things and just a whole lot easier to read and debug as well. Okay, all right. So this is an example. If the input string is just 1582 without anything, then the sign should be a 1 because it is a non-negative or positive number. M, which is the mantissa without the decimal point, is exactly the same number here because we only have the mantissa, we don't have an exponent component. And then the default component for the default exponent in base 10 is a 0 because the value represented by the number is the sign times the mantissa times 10 to the power of the exponent in base 10. So in this case, if the number is 1582, the sign is 1, which doesn't do a single thing because 1 times whatever is whatever. The mantissa is 1582. Okay, that's fine, we put it here. And then exponent is not specified, which has a default of 0. 10 to the power of 0 is 1, which doesn't change the value at all. So we still get 1582 back as V in this case, which is the value that we are representing. Is that okay? Okay, moving on to the second example. -4.78E3 is parsed so that the sign is a -1, and also we want the mantissa in this case to be 478 because as I said, the mantissa in this particular structure is the same number here except you remove the decimal point. But if you remove the decimal point, doesn't that change the order of magnitude? The answer is yes, it does. But that's why we are compensating it by making the E into a 1, because even though it is a 3 here, we have to adjust it by 2 because of the decimal point here. Is that making any sense? No? Okay. I was trying to attempting a fast one here. Okay. So when you look at 478 times 10 to the power of 1, isn't that the same thing as 4d7.8 times 10 to the power of 2? Which is also the same as 4.78 times 10 to the power of 3. So by shifting this decimal point all the way to the right-hand side of the 8, I have to adjust the e so that the value represented will still be the same. Is that okay?
Yeah.
Because in the end, I just want the value to be the same as what the string is representing. But because m itself is an unsigned integer, it cannot represent the decimal point. So I have to take care of the decimal point by adjusting the exponent. Is that okay? All right. So the next example illustrates that as well. Because in this case, this number is a non-negative number, and that's why the sign is a 1. The mantissa is originally 2.5, but since I really don't care about the decimal point, it becomes 25. But in order to compensate for not adjusting for the decimal point here, I have to change the exponent from -1 to -2 so that it is, so when I look at this value, which is 2.5 divided by 10, which is 0.25, and then when you look at 1 times 25 times 10 to the power of -2, it is also 0.25. Is that okay? So by calling 3 different subroutines, one to deal with the sign, one to deal with the mantissa, and one to deal with the exponent, I get these members of the structure populated. So once these particular members, let me point out which ones we are talking about. So once we have these members populated, then we can start the actual conversion. Is that okay? All right? Okay. So when you do the parsing, I just want to bring out some tricks that you can do. You definitely want to increment the pointer quite a bit. Every time you recognize a character and say, hey, this is the right place for this character to appear, and it means la 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 la. Once you recognize and process the character, increment the pointer so that you are ready for the next thing to process. On the other hand, you're at a place and you say, I'm only expecting a plus or a minus, and you see something else, do not process anything. And then use whatever is the default that should go into that position. Does that make any sense? When you get to the e, okay, so the subroutine that is processing the exponent, and you say, I'm expecting a lowercase e here, and you don't see a lowercase e, just say, okay, by default, the exponent is a 0. But if you do recognize an e, then you have to say, okay, I recognize the e, I will proceed to expect digits. Okay, and then you process the digits, and those digits will become the actual exponent. Are we okay so far? Okay, all right. So the first part is really, not so much related to the representation of a number in binary, but to parse a number represented in scientific notation so that you end up with something like this so that we can process that using the following logic. Okay, so the conversion process, okay, it is kind of important to emphasize what we are converting. What we are really converting is this, okay, this equation here shows exactly what we are trying to do. The value that we are trying to, oops, okay, I keep doing that. Okay, so what we are really doing is exactly the same thing. V has not changed, okay, because we're still representing exactly the same value. The lowercase sme, okay, s times m times 10 to the power of e, that is coming from your scientific notation. This is coming from your string. Is that okay? The uppercase m and the uppercase e are the ones in binary. That is where the conversion is. The conversion is how do we go from lowercase m and lowercase e to uppercase m and uppercase e so that these two products end up with the same value that is being represented. Is that part okay? All right. How come lowercase s is still lowercase s? That's just a sign. It's the same, right? So we can just use the same sign. Okay, so that's why that part is not converted. All right. Are there any questions up to this point? Questions? Okay. All right, so the next one, then we have two subcases. The first question is, what if E is less than 0? And then the next one talks about what if E is greater than or equal to 0. Okay, because which way E is determines what algorithm, what you need to do. Are you dividing by 10 or are you multiplying by 10? That's what the impact of E does that. All right, so let's go ahead and when E is less than 0, it's not really a problem. It is just a little bit more challenging mentally than the other one. So when E is less than 0, okay, when we go back to here, we are basically multiplying something by 10 to the power of some negative power, okay, which is the same thing as dividing by 10, right? So we do have to divide by 10, but remember, in your subroutine, in your ATOF, you cannot use double or float. You have to use all integer math. So you cannot use log. If you can use log, the problem is solved like in 2 steps. Yeah. Okay, so what do we do here? So the problem is, you have to do division by 10, but how do you do division by 10 without losing things? Okay, so the first thing we want to do is to say, okay, what if this is a simple one? Okay, if the division results in if the division results in a 0 remainder, it's easy to do. In other words, okay, let me see if this makes sense here. Okay, I think I missed slide here. Okay, so because we have to divide it by 10, if you divide by 10 and it's an even division, which means there's no remainder, that's the easy one to deal with. On the other hand, if you have to divide by 10 and there's no way you can make it so that there's no remainder, no matter what p you choose here, it will still have a remainder, then it seems like we have a problem. So we skip here because you can go through this discussion here, but what I'll do is I'm going to jump all the way to the part that does matter. Okay. So let's go ahead and start with this one, because this is a key word or key phrase to basically say if you don't have enough time, skip to this part, right? Every time it says, anyone says in conclusion or in summary, okay, that means well, you have just wasted your time reading all the stuff before this point. But this is a good starting point if you don't have enough time, and if you do have enough time, read the portion before, because it explains the rationale of how we get to this point. Okay, to handle the case when E is less than 0, remember E is an integer, so it's -1, -2, and so on. In this case, division by 10 is inevitable, cannot be avoided. But for the ith division by 10, we can find a p subscript I such that d subscript I is da 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 da. Okay, so a few explanations here. We are only dividing by 10 one step at a time. In other words, even if E is -5, you do not say, oh, I know 10 to the power of 5 is 100,000, so we'll just divide it by 100,000. Nope, that's not how we do it. We divide it by 10 in each step. So you divide it by 10, and then you divide it by 10, then you divide it by 10, then you divide it by 10. But there's something in between that you're doing to help to keep your representation precise. Now, what do I mean? What do I mean by precision? Let's try 13. Okay. If I want to represent 13 as a 13 may not be a good one. Okay, 13 is a good one. Okay, because yeah, it is a good one because we want to represent, let's say, 13 times 10 to the power of, say, -2. Okay. Right. So it's 0.13, right? But 0.13 turns out to be one of those values cannot be easily represented in binary. It's just like trying to represent 1 divided by 3 in base 10. It becomes 0.3333. Okay, so it's a recurring pattern. Okay, so how do we deal with that? That's the question. If I just say, oh, we can just divide 13 by 100, it's useless because this will give you a result of 0 because this is integer division. Remember, you cannot use floating point or double math, which means this is now limited to an integer division. In an integer division, 13 divided by 100 is a 0. Well, that's not what we want. Okay, so how do we do it? So the way we do this is we say, okay, we look at 13 divided by 10, and even this is not very helpful because it is 1 instead of 1.3, right? So your error is 30% in this case. That is not good. Okay, so this is not what we want to do either. So what we want to do is to extend the numerator as much as we can. So it becomes a large number, and then divide that by 10. So we end up with a really big quotient, right? And that will preserve the precision of the result. Okay, so we'll say, okay, we'll look at this as 13, and then we say, I'm just picking a number here, okay? So later on we'll talk about how to pick that number. How about this? Don't you think this number is pretty big? 13 times 2 to the power of 16, that's a pretty big number. And you divide it by 10, the result is going to be off by something. But it cannot be off by any more than 5. Okay, we'll do rounding later on. Okay? So 5 out of this value is a whole lot better than 5 out of this value. Is that making any sense? In other words, we want to scale the numerator up to minimize the error margin after the division. But that is going to change the value of the number, right? So what we need to do is to remember, hey, we tweaked the whole thing. We introduced a 2 to the power of 16 in this case. So on the side here, we just remember this is P1, this is the first step. So we remember P1 is 16. We keep track of how we pad a whole bunch of pad a power of 2 to make the numerator as big as we can before we divide it by 10. Is that okay? All right. Okay. So in this case, we say P1 equals to 16, and this 16 is not actually 16. It is actually supposed to be a lot more than that. But we'll figure that out later. After the division, you end up with a quotient, right? Okay, so we'll say the quotient is, there's a particular notation I use in here. This is DI. Yeah, okay, so this is DI. So DI is this portion. And then we have to do some rounding. So the rounding has to do with CI. Okay, so CI is basically, it can go in two different directions. If DI mod, okay, I'm using the C notation mod here so that you know which operator to use for mod. How many people have not seen the mod operator in your C++ class in 360? No one. Okay, I did all this work for nothing. Okay, that's okay. That's okay. Not that I'm pissed at you anyway. Okay, it's good. It's a good thing that you guys have all been exposed to the mod operator. Okay, so when this is at least 5, okay, then CI is a 1. And if DI mod 10 is less than 5, then C1 is a 0. Okay? So the whole purpose of CI and DI is to set up M2 in this case. Oh, this is M1. So M1 is just DI, D1. This is 1. This is the first iteration. That's why there's a 1 here. So there's a 1 here minus C plus C1 here.
Plus.
That's also C1 here. And this is C1, D1, and D1. There we go. But in the description, I just use an I to make it more general. Okay? Can everybody understand what this C1 is really doing? Without C1, then the error is always making the representation smaller than what it is supposed to. Every single time, I'm losing something. by using CI, I'm keeping it, sometimes it's less than what it is, sometimes it's more than what it is. So I'm basically removing a bias in this type of calculation. Is that making any sense or not? Because otherwise, if I don't use the C1, here, I'm always truncating the number. I'm not rounding the number, I'm truncating it. Okay, that's the difference between taking the floor of a value as opposed to rounding a value. The floor of a number, okay, some of you might have seen the symbol, the floor. The floor of 0.8 is 0. The floor of 0.1 is also 0. So if the default behavior of integer division is taking the floor, that means whenever I have an error, it's always losing something. I keep losing something in every single step. But these steps are cumulative. So that means if I have a bias, if I have one single bias in one single direction, I will keep losing something. So the end result is going to be quite a bit smaller than what it is supposed to.
Yeah. So this is just, okay, so it's when you mod it, if C1 or D1 is closer to, it's basically going to pop it back up or down,
Yep.
whichever one's closer to.
Yep.
Okay.
Exactly. So this one, make sure that I don't have any inherent bias in the process. Am I still losing precision? Yes. But at least it's not always in one single direction. Okay? So are there any questions about this step, this process? So the key is you have to track the powers. So once we have figured out what is M1, what do we do with M1? Well, we ask, do we have another division by 10? Do we have another division by 10? Yes, we do, because we just took care of only one of the 2 tenths that we had to divide. So what do? Well, we repeat the same process. So we have to basically look at D2, and D2 is based on M1, and we want to multiply a power of 2 that is really big. Okay, once again, I'm only choosing 16, as just a number out of thin air. Okay, but later on we'll find out how to figure this out. Okay, and then we'll do the same thing. Okay, so this is D2, and then we look at there's a division by 2. Oops, I think I made a mistake, because division by 2 is not factored in to DI. So DI needs to okay, I know where I'm missing the item here. This is not supposed to be DI, this is supposed to be DI divided, integer division by 10. And the CI is designed to be a rounding constant. So let me change this first, and then we'll go back to this slide. Because this is one thing that is really important. I cannot leave it like this and explain it the way it is. So let me sign in to machine. So here we have it. There we go. Okay, so I think that should be it. I'm going to keep the editor up on the other side. Oops, I need to do this. There we go, and update on this side. There we go, now it's correct. So MI is DI divided by 10 plus CI, and that division is an integer division. In other words, it truncates the fractional part. Is that okay? All right, so that's good, because then I need to update what is on the whiteboard. So DI is actually this entire part. Is that okay? And
That's DI.
Huh?
That's DI.
That's D1. Yeah, this is D1, but it's actually this entire part. And then M1 is still D1 plus So, okay, I see. Okay. So we'll keep di just this part, and then m1 is d1 divided by 10, and the floor of that plus c1. So now it's consistent with the notes.
So it's under a condition, right?
Hmm?
If the di mod is 10 or less than or equal to 5, it's under a condition or not?
Right, that's C1. C1 depends on whether the mod is, when you mod D1 with 10, if the remainder is at least 5, then you want to add 1 to M1. If it is less than 5, then you don't want to add 1 to M1. Okay? So the whiteboard is now consistent with the notes. Okay, so now we get to D2. So D2 depends on M1, and you do exactly the same thing. And this time you may not want to use as big of a value. So once you set it up, you probably are going to alternate between 3 and 4. The reason why you're going to alternate between 3 and 4 is because 10 is between 2 to the power of 3 and 2 to the power of 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. So every time you divide a number by 10, okay, sometimes it will drop below the point where you have to multiply by 16 again to bump it back up again. Sometimes it won't drop below that point, so you only have to multiply by 8 to bring it back to the same point. Because we want to basically populate 64 bits all the time in order to minimize the error. Is that okay? So this is just an example. So D2 is M1 times 2 to the power 4. We'll just use this as an example. And then we have to figure out what is C2. So C2 in this case is basically the same thing. It's a 1, but only if D2 mod 10 is at least 5. It's going to be a 0 if D2 mod 10 is less than 5. Same thing, same equation. Okay? Because C2 is really just for taking care of rounding. And then M2, in this case, is going to be the floor of D2 divided by 10 plus C2. And the floor of the division is automatic when you are using integer division. So integer division is automatically taking the floor. So you don't have to use a floor function at all. But mathematically, it is important to use a floor function to make sure that we're only keeping the whole number part and ignoring the fractional part. Is that okay? Or not?
It's gonna be easier if we have this is theoretical part what we're doing, and here
Right.
would be like the mathematical representation of it, so we can track okay, this step with the division, that's what we do.
Okay, all right, I understand that. Okay, so let's do this using a spreadsheet, because I can actually do everything as a spreadsheet. The best part about a spreadsheet is once you look into the formula or formulae in the spreadsheet, you can pretty much piece together what you need to do to get it to work. Okay? It still needs quite a bit of thinking on your part, but it does make it easier. Okay, so we'll do it with a spreadsheet and illustrate it. And I will go to the spreadsheet I will go to a folder that is already shared with this class. So this way you guys can follow along if you want to. So I'm going to put this as an example, put it here as a spreadsheet. And we'll call this double conversion. Okay, so we name double conversion. There we go. All right. So we'll go ahead and start with the assumptions. The assumption is what is S, what is M, and what is E. And we'll use exactly the same example as on the whiteboard, so this way it's consistent. So we have S being a 1 because it's a positive number, M is 13, and E is -2. So the value that we really want to represent, which is V, is, I can just use the equation that is in the notes. Let me go back to the notes and show you which equation we are talking about. Okay, that's not it. Okay, so the equation that I'm talking about is how do we compute this V here. So we'll go ahead and just show you the value. And it is in, okay, where's my, Oh, here. Just have to put them next to each other so it's easier for me to click. Okay, so it is the sine times the mantissa times 10 to the power of the exponent. So the value that we want to represent is 0.13, or what we know as 0.13 in base 10. Okay? But we want to change it so that we are using powers of 2 as opposed to powers of 10 for the exponent. That is the tricky part. How do we do that? Okay? All right. So we'll go ahead and start with the different iterations. So here's, well, let me see if I can need a different sheet here. Probably need a different sheet. Okay, so in sheet 1, we have iterations, and this is iteration 1. So in iteration 1, okay, oh, by the way, m is the same thing as m subscript 0, okay, which is the m before any iteration happens. So in iteration 1, we want to figure out what is P1. Okay, what is going to be the P1? Because we want P1 to be as large as possible without overflowing a 64-bit unsigned integer. In other words, we are looking at this value here. Instead of randomly picking a 16 here, we want to say, what can we put here, which is denoted by P1, so that the product of 13 and 2 to the power of P1 is just a little bit less than what a 64-bit number can represent. Because this way we maximize the precision so that we don't lose information in the process. Is that okay? So we want this number to be just a little bit less than 2 to the power of 64 in this case. So now the question is, without using log, how can you do this? How can you figure out what P1 is supposed to be? You cannot use log because that's a floating point number library. So without using power, how do you do this? Okay, let me show you something, and you guys can say, is that going to work? So we start off with 13, right? And then we say, well, what about 2 times this? That's 26. And from here on, we can just go like that. Because each one is basically just 2 times the previous one, right? So the question is, when do we stop? Well, we know that this cannot go on for more than 64 steps. Because if I started off with 1 times 2 to the power of 64 is already exceeding the limit, right? Okay. But we still need to check whether we should stop or not, okay? So what we'll do on this side here, is to have a condition to see, okay, should we quit or not? So we say if this number is greater than or equal to the power 2 to the power of 64, because we are choosing 64-bit unsigned integer in this case, then we say stop. Otherwise, we say go on. Okay. All right. And the best part about using a spreadsheet like this is I can be lazy. Like really lazy. And just keep doing like this. Well, it's a 64-bit number, so it does go on quite a bit. I think it's a little bit too much. Oh, stop. Okay, very good. Okay, so it does tell me when to stop. So that means, I can, okay, what is this telling you? You cannot use, floating point calculation. Did I use any floating point calculations? Okay, this is just multiplication by 2, integer math, right? Oh, but what about this? There's a power function here. You can use multiplication, but there are constants as well. So there are constants that you can use to tell you what is the largest value you can actually represent. Okay? Is that making any sense? Now, because we're dealing with unsigned integers, right? 0 minus 1 will give you the largest value that can be represented. because we are using unsigned integers for the mantissa, right? So that means what we're comparing against is also an unsigned integer. Well, with an unsigned integer, 0 minus 1 is the largest possible value that you can represent. Remember the number wheel, right? If you go on one side, it's 1, 2, 3, right? When you go to the other side, it is the largest possible value. When you rotate a wheel, it doesn't really matter whether you're crossing that line of 0 or not. The wheel is turned basically the same way anyway. Is that making any sense? No? Sort of? Okay, so let's check that theory, because I like to confirm the theory before we actually use it. So we'll just go to GDB and check it. So we say, what is unsigned long, okay, because we have to cast the 0 to unsigned long to make sure it's 64-bit. So that minus 1, there you go. Because we casted the 0 into an unsigned long, which is a 64-bit integer, and we subtract 1 from it. So you would think, well, 0 minus 1 should be -1. Well, but this is an unsigned integer, so we don't have -1. Instead of representing -1, the same bit pattern is representing 2 to the power of 64 minus 1. The hexadecimal representation, guess what it is? Yep. All F's. 16 F's, in fact. Is that okay? And we'll double check and make sure that it is, in fact, 16 F's. Yep, there we go. Now you know why I like command line tools. GDB, Swiss Army knife. If there's such a thing, as a MacGyver developer, this is the tool that MacGyver wants to use. If you can, who's MacGyver? Okay, good question. And the rest of the class said, why did you have to ask that question? Yep, that's when he's young. Richard Dean Anderson when he's younger. Yep. So I'm pretty sure you can find episodes online. He's a very non-violent guy who has to get into kind of dangerous and adversarial situations and deal with problems, people, and all kinds of stuff. So you always find a really smart way to solve difficult problems. Sorry?
He jerry-rigged everything.
He?
MacGyver did. Jerry-rigged.
Oh, jury-rig. Yep. Jury-rig everything. He is the original hacker. I wonder why they don't use him as the poster boy or man or old man of Hacker Lab, because that would be pretty appropriate. I guess his role in SG-1 kind of destroyed that image. It's like, what problem? Shoot it. Okay, so what we see here is, this is really important because we see if, you can use an if in a spreadsheet. It's basically a ternary operator where you can have three things. The first one is a condition, and then if the condition is true, it returns whatever is in the middle. If it is false, it returns the last thing. So the same thing as a ternary operator in C and C++. Okay, but there's a condition here, and it seems like I'm doing something until a certain condition is true, then I stop, right? So you kind of have to map what I'm doing here with constructs in C and C++. Okay, there are only so many constructs in C and C++. Okay, and certain ones really does not make sense in this case, so I can help you rule out what does not work in this case. A switch statement probably is not what you need in this case. Okay, but from here we can tell a few things, okay? Because when we do stop, okay, which means this is the row that we want to throw out because it's already exceeding the range. So we have to keep everything up to here. So that means this is my D1. Okay, so let's go ahead and remember that. So we say this is the iteration, this is DI. Okay, and the best thing about the spreadsheet is I can refer to values of another sheet from any sheet. Okay, that's kind of cool. I can also remember what is PI. PI is the power of 2 to pad. So when I stop, so that would be, oh, this is going to be. It's not 61. I think it's 60 because the first row has no multiplication by 2. So we can. I suppose we can do this. We can say what is the row number of this guy? -1. Okay, we got PI. And then we have, what else? CI, okay? So we have to compute CI. Okay, so now when we compute CI, do you guys remember what CI, how CI is computed? Is D1, okay, divided by 10, and then we look at the mod. If it's more than 5, it is 1. If it's less than 5, it is a 0, okay? So we can do it with a spreadsheet as well, okay? So now we say if this thing, oops, okay, back up. If the mod of this thing and 10 is greater than or equal to 5, then we want it to be a 1, otherwise we want it to be a 0. Okay, what am I missing here? Parameters in mod is out of range. Okay. The error occurs when the following is true, the divisor blah 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 is less than or equal to the dividend. Darn it. Okay, cannot do this. Well, we can do. Let's see. Do we have fraction? Nope, but we have floor. Okay. Well, the effect is the same. I'm going to use a different logic here. So we can say the same thing by claiming if this thing divided by 2 minus the floor of the same thing, B5 divided by floor. If this whole thing is greater than or equal to 0.5, then we want that. Okay, so let's put extra parentheses here. You don't need to do this, okay? I have to do this only because it doesn't have, the mod doesn't work in this case. Is that okay? I have a really bad suspicion that this is going to be a 0 all the time because I don't think it tracks 64-bit numbers in this spreadsheet. I may be wrong, but we'll double check. Because the only way to check that is to change the whole format here so it doesn't use the scientific notation. We don't want scientific notation, we just want it to be a number. Yeah, that's a problem. Because it is, yeah, it's a problem because it has run out of precision by this time already. But so you can see how it's just multiplying by 2. No, that's not multiplication by 2. What is going on here? Pardon? Sorry? Does it look right to you? 266 times 2 is 532. But I cannot explain this one. 82 times 2 is not 65, so something is not right here. I don't know whether this is the exact value that it's tracking or not. Oh, limitations of a spreadsheet. Okay.
Can we just use the 16 for P1 just to see how it works?
Okay, we can do that. Okay, so if we wanted to use 16, then the go on condition is going to terminate a little bit faster. Okay, so basically we're just changing this part and say, okay, we'll just pretend that we are using 16-bit unsigned integers, right? So we just have to propagate this. That won't take long, because, oh, I forgot to do the 2 times here. 2 times that. There we go. There we go. Yep, so it stops here. That means we use this as our row. Okay. So DI is this one, and then PI is the row number of that one, minus 1. It's the row number of this one. Okay, it's reporting it's 13, but we know it's just, we have to subtract 1. And then this one may work now, because we can use mod again. Okay, so we say mod this number, oops, wrong place. Mod B5 with 10. That is at least 5. And we want it to be a 1. There we go. So that works. So I'm basically making the problem a lot smaller. Instead of using a 64-bit number, I'm turning it into a 16-bit number. But the approach is the same. Okay? All right. So that finishes the first iteration. And on the second iteration, we basically start with whatever is we end up in the first iteration, but we have to divide it by 10 first. And then we figure out, how much to pad it. Is that making any sense? Okay. So we basically say, okay, so we have to figure out what is M1 here. So M1 is this number, so we'll go ahead and represent that. So M1, or this is MI. MI is this number divided by 10, but it's the floor because in this case the spreadsheet uses actual division and not just floor division. So I have to take the floor function by hand, and then plus CI, which is this one here. I'm using the equation.
Will mod work?
Huh?
Mod function will work in this case?
Mod?
Yeah, because we're using floor numbers.
No, mod won't work in this case. Because we still want to use a floor function. We only care about the whole number part of the division. Yep.
Floor division is essentially integer division, right?
The floor of division is the same thing as an integer division. Yeah. So that's why in your case it's going to be a lot easier because an integer division automatically takes the floor of the result.
So it truncates it basically.
Yep, it's truncation. Yep. Mm-hmm. Well, it's not exactly truncation because when you have a negative number, floor is different. But since we're dealing with unsigned, it's fine. Yeah. Mm-hmm. Okay. So DI, we need to figure out what is DI. So I'm going to use another spreadsheet to do DI. In this case, so in this case, spreadsheet number 2. Oh, okay. I just dragged it. There we go. So this number, the start value of this is M1, which is this one here. And then we have to use the same condition, of going on. So we'll use the same condition here. And then we say the next one is 2 times this one. And then we ask the question, should we stop now? Well, we kind of know that 16-bit integers can represent up to like 64K or so. So we know, we probably can we can do at least 2 more. Okay, still go on. The next one is going to fail because this is more than 65,536. So now we have to stop. This number becomes our DI. So this becomes that. Okay. And then this is the row number of this guy, minus 1. That becomes my PI. This one we can just borrow. We can just copy, and then this one we can just copy as well. There we go. Are we doing okay so far with this? Still okay? More or less.
Yeah.
Okay. So, but we are done because because the exponent is only minus 2, so that means we only have to perform this in 2 iterations, because the objective is we have to divide by 10 twice. But we don't want to just divide by 10 because that can lead to a loss of precision. So instead of just dividing by 10, we are bumping up the numerator as much as we can using a power of 2. Okay? But then we have to remember how much we have padded. So that's what the PI column is for. We have padded 2 to the power of 15 into this whole calculation. Is that okay? Sort of? Okay. Okay. So we want to check the sanity of all of this stuff here. In other words, are we still representing 0.13? I don't know. Let's check. Okay. So we wanted to figure out what is V again. And this time we have the same thing. Sign is exactly the same as before. Okay, fine. Oops, clicked the wrong thing. Equals that. Okay, and then we have to look at the mantissa. Our mantissa is this guy here. This is our current mantissa. And then we have to also multiply that by the exponent. But the exponent is no longer an exponent of 10. It is now an exponent of 2. Okay, very good. So we have an exponent of 2. And what is our actual power? How many powers of 2 have we padded in all the calculations? The summation of all the p's, so we have 15, right? So we have minus 15 here because we have to compensate for that. Because every time you multiply something on the numerator, you basically have to multiply the same thing in the denominator. Except I'm not putting it here, I'm just remembering that. And then we'll use the exponent to adjust for that. Okay? So let's see if that is the case. Well, pretty darn close. Are we done? No, not really. We are not quite done, but we are very close, okay? Because what we have done at this point is we have changed the exponent of 10 to an exponent of 2. The rest is all about bit shifting and stuff like that, okay? All right, so let's go ahead and see what we have to do in bit shifting. I don't think we have enough space in the spreadsheet to do this, but we'll see. We'll see if we can actually do that. Okay, so we are looking at this as the mantissa. Does this look at a number that is between 1 and 2 to you? No. So that means we have to do a whole bunch of shifting so that it is a number between 1 and 2. Okay? So the question is, how many times do we have to shift it? Now, you don't really have to do that in your code, because in your code, basically what you want to do is to look at this number and you ask, we want this to be a 1 followed by 52 digits. So we want to shift it until the most significant bit is bit 52 of an integer. Because your mantissa, you guys do remember how the mantissa is represented. The mantissa is 1 point blah, 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 right? But we do not represent this 1 point, okay? That part is implicit. We do not represent it explicitly. So what you're really representing is this part here. In a double precision floating point number, bit 0 is this particular bit, and then this is bit 51. So you have 52 bits altogether to represent the digits to the right-hand side of the point. Is that okay? So what we want to do is to look at the binary representation of 4260, which is going to be only about here, and we want to shift it. We keep shifting it until it fits into this format, until the 1 is occupying bit 52. Is that making any sense? But we have to remember how many times we have to do it. So once again, we can use the same method to figure out how many times we have to shift it. So in sheet 4, I will perform that particular test. So you can see that I'm not using any magical function. I'm just using a control structure to get this done. So now I look at E6. Okay, so we start with sheet 1, E6. and then we say, okay, how many times do we have to multiply this until it is just at least 2 to the power of 52, because that's the value that we want, okay? So we say, if, okay, we can actually just copy it from here. Okay, copy, paste, except this time it is 2 to the power 52, and the logic is also entirely different, because when it does get to at least that, okay, it is correct. Okay, so we stop when it's at least this much, otherwise we keep going. Okay, so next one is 2 times the one before, and this one is just a straight copy. There we go. Whoops. Drag. There we go. So now we can just drag this on. It's going to be 50 something times for sure. Okay, so this is the last number. Is that okay? So what that means, I'm not sure whether the spreadsheet can do this or not. Okay, so in the spreadsheet here, we can say the binary mantissa is the following. It's going to be this thing here. Copy and paste. Function multiply parameter. Okay, I'm not multiplying. Okay. Equals. Equals. Oh, okay, it's covering what I need. Oh, no, it's right here. Got it. Enter, there we go. Okay, so we want to convert this into binary and see whether it is taking up 53 digits, because it's 1 followed by 52 digits, right? Do you think the spreadsheet can handle this? Deck to bin, and this is what we're converting. Nope, doesn't like it. It just won't do it. Okay. But basically, this is supposed to be the mantissa. Now, so what we have done here is we have shifted 4260 all the way out here. So depending on how many times we have shifted, we have to take that into consideration too. Yep.
Can you use the GBD to do that?
Can we use GDB?
Yeah.
Yeah, we can use GDB, but GDB cannot. I cannot specify the logic to do this part of the calculation. Oh, but we can do a.
You just pop it over binary information.
Yeah.
Sorry?
Can you just have it display that in binary, or?
I think so. We might need to convert it back into a number format first.
Decimal to binary calculator.
We can do this in. We just have to convert it into a number, plain text, automatic, or formats. Whoops. Custom number format. There we go. Okay. So this is exactly what we want. Oh, it is. Looks like a pretty good number here. So Control C, go back to GDB, and to print it in binary, it's a /t if I remember correctly. So, does anyone want to count whether there are 51 digits or not?
We can paste it back to Excel, let it count the length.
Yes, we can. Or we can print it in hexadecimal, so it's easier to count. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that accounts for 48 bits. And then the 8 is requiring 4 bits. 48 plus 4 is 52. And that's what we want. Yep. Let me double check. I'm self-doubting. I think we're missing 1 digit.
51, so isn't that what we want, 52 digits?
It's 50.
No, the decimal right there, from 0 to 51, so we want 52 digits, right?
Hmm. 2 to the power 52, because we want a 1 here, and this is bit 52, so that means the value is 2 to the power 52 or more. So the condition of stopping is correct. So that value is probably correct. But because we have to shift it 40 times to take care of this, that means we have another 40 to deal with. So when we go back here, so we have another shifting of 42 bits, right? Because we keep multiplying those things, we have another 40 bits here. But then there's one more thing that we have to do, because when you look at that huge number, when you look at, okay, let me switch back to the debugger. When you look at this number, this is not a, does this look like a value that's between 1 and 2 to you? No, because the implicit 0 is where? Right here. How do we turn this into a value that is between 1 and 2? Shift it once, 2, how many times? How many times do we have to shift the period all the way from here up to here? 52 times, okay? So in order to shift that 52 times, how are we impacting the exponent of 2? Every time we shift it, we have to multiply by 2. Okay? So that means, back in the spreadsheet here, this is actually, all of these are negative. In other words, this is a negative 12. This is a negative 3, because in order to compensate for multiplication, all of these are on the denominator. So that's why these are all negative. So altogether we have a we have this many bits. What? Oh, okay. One more time, just some. So we have 55 bits, of shifting that is negative. So if I just put a negative sign here, okay, and then we have 52 bits, in the opposite direction. So that means the net shift that we need is this number plus this number. So the net shift that we need is actually only negative 3. Does that make sense? I'm just checking because basically what we are looking for is 1 divided by 8. Is that close to 0.13? And the answer is yes. Okay, so we still have all the calculations correct so far. It's just a sanity check. Okay, so now we have this point, negative 3 here. This negative 3 is the power of 2. So we want to double check again. Okay, so now we want to look at V again. It is the sine, right, times the binary mantissa. Oh, what did I do? Okay, so this is the sine times the binary mantissa times, then we have to do all the shifting. So this is taking into consideration the shifting of the binary point. So it's power 2 and then 0 minus this value. Okay, and then the actual exponent is this one here. So we have to multiply this by the power 2 to the power of negative 3, like so. And we are off by 1. We are off by 2. So we are losing that 1 somewhere. And I know this 40 is off. Okay. Because it is row 40, which means we only shifted 30. We have shifted only 39 times. That's why. Okay. This is supposed to be 39. Then it's correct. Yep. But have we figured out all the bit patterns yet? This is the bit pattern for This is not the entire bit pattern because this one is not represented. So we have to remove the most significant bit of this number. Then it becomes bit 0 to bit 51. What about the exponent? Do you guys still remember how the exponent is represented? The actual exponent value, which is 2 to the power of something, is e minus 1023, right? And we want this entire expression to be -3. So we want -3 to be e minus 1023. So you add 1023 to the other side. So e is 1020. Right? Okay. So e, the exponent in base 2, e is 1020. So we will do the conversion here. It's decimal to binary, and it's 1020. I think it can specify the number of digits required. So we'll specify exactly 11 digits. No, doesn't like that. It doesn't like that conversion because it's not a value between -512 and 511. Okay. Back to the debugger. Binary, and this is 1020. So we just have to pad a 0 at the front, then it becomes an 11-bit number. Okay, so this is actually a good view, by the way. This is actually a good view because what it's telling us is this part here is bit 0 to bit 51. That's the fraction part of the mantissa. Okay. This part here, imagine there's a 1 as the most significant bit to make up 11 bits. That would be bit 52 to bit 62 because that's the exponent. And then we have a 1, we have a 0 for bit 63 because the number is a positive number. Okay. I know we're running out of time. I know you're anxious to kind of go home and stuff. But we want to double check. We really want to double check all of this stuff here to make sure that it is all working. So what we need to do then is to use this thing here to help us out. It's just remembering the numbers. Okay. Oh, but I can't change the. Okay, let's see what can we do. Nope, the other way around. There we go. Okay, so what I want to do, well, okay, we can just copy and paste for the most part. So we'll copy this and paste it here. That should account for 52 bits. And then we have this bunch here. And that combined with an 0 up here. And then we have a 0 all the way up here. That should be the binary representation of 0.13. Well, we lost precision because we only limited ourselves to 16-bit. Okay, but if we did not, then we will have like a repeating pattern here. Okay, so let's count the bits. 4, 4, 4, 4. Nope, we lost 1 bit. This one should be at the boundary, so we lost 1. So when we did the conversion in the spreadsheet, it was off. And so that means it really should not stop here. It should probably stop here. That's why we got off by 1. Why would it complain and stop here? Yep.
I don't know. When you copied the number from the GDU, you skipped copying the 1. Did you do that on purpose?
The first one.
The first one?
Oh yeah, 52-bit 52.
And the 52-bit number?
Yeah.
You didn't copy the most significant, the 1. And the
Yes, I did it on purpose.
Okay.
Because the 1 the one to the left-hand side of the point is implicit. So that is not actually represented in the 64-bit of a double precision format. So that's why it's never represented. But the question is, the question for myself is why is it stopping too early? That's the problem. It's stopping one step too early. This is comparing to 2 to the power of 52, which is 1 shifted by 52 times, which should be bit 52. I know exactly why, because we stop when it is that. That's why. Okay. Okay, so we'll just go ahead and propagate these again. We kind of know what the answer is supposed to be because we just stopped one step too early. That's all. Okay. So we'll go ahead and change this one more time. And this one is, it's 41 bits. Okay, so this is now 40. There we go. Okay, so now it should be better. We still have to look at this number as just a regular number. So we have to format the number to just a regular number like that. Control C. It's basically just padding 1 zeros, on the other side. Okay. Paste. Okay, you can see how these two numbers are basically the same. It's just that one has one additional 0 on this side. It's basically the same thing. So now this becomes here. Yeah, just have a 0 padding all the way to the least significant side. Okay, so but it should be the correct number now. Yep. Okay, that's good. We are almost there. Almost. Okay, so now we want to represent this number as a hexadecimal number, so that becomes a 3FC0 A4, and then a bunch of zeros 1, 2, 3, 4, 5, 6 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is the binary representation. When we cast this back into a double precision number, that should give us what we need. All right. I know you guys want to go home, but we are really close. So let's go ahead and check this one more time. There we go. Make clean. Make GDB, and we can put a breakpoint at line 8, run, and then we can say set var u.I equals to this thing here, paste, there we go. Left operand of assignment is not an L value. Great. Optimized out. No. Okay. But wait, I can do this fast. Long unsigned x. X equals 0. X gets x plus 1. Return 0. Okay, gcc-g-g-o test GDB test. There we go. Put a breakpoint on line 6. Run the program. Okay, now we can do it. So we can now say set var x equals to the same thing. Paste. There we go. Print. Do you remember that trick? We cast the pointer.
Yeah.
Complaints about.
Parentheses.
Oh, missing one. Paren. There we go. There we go. No, but do you guys understand the whole process?
Yeah.
Yes, sort of. One more time. So the most important part is to figure out the P1 because you need to pad the number so that it is as big as possible so that when you divide that number by 10, you're not going to lose a lot of precision. That is the biggest trick is that. And then you just have to keep track of all of these compensation so that you know at the end how much to adjust the exponent to take care of that. Is that okay? All right. Oof. Okay. So the notes, it actually does contain all the stuff that I just talked about. It's just that with an example, it's a little bit more visible. So go ahead and try to see if you can write this program. The spreadsheet, you can access the spreadsheet already. It's on my Google Drive.
It is on Google Drive on examples.
Yeah, it's on the Google Drive. It's under the folder called examples, and it's called double conversion. Yep. And you can take the picture of the whiteboard too if you want to. Just make sure I'm not in the picture or blur me out.
Yeah. I asked my dad if he had seen that show Babylon 5, and he had all the DVDs, and he made me borrow them to watch them. It's